So welcome to the Data Science Speaker Series at the University of San Francisco, sponsored by the Data Institute. As you all know, Data Institute is our umbrella organization for all things data science at USF. Our speaker today is Matt Wheeler, an MSDS alumni from about 2 cohorts ago, and a current PG&E data scientist. Today's talk will be exploring the broad scope of data science as a whole and highlighting the flexibility required on smaller teams to manage tasks spanning data science, data engineering, and machine learning engineering.
Savannah?
Yeah.
Okay, great. Yeah, it's great to be here. It's very strange to be standing up here saying that maybe 2 years ago, I think sitting where you guys were, the previous one I was saying now, it felt like only yesterday when he was here, and it feels like that same right now. So I'm sure some of you in the crowd will be back in a couple of years saying the exact same thing. Before I jump into the book that Victor just described, I thought it would be useful to describe a little bit about my background and how I came about sort of approaching data science. So, yeah, I hope my accent hasn't completely gone yet, and you can tell that I'm originally from the UK. Specifically, I'm from Wales, which, if anyone doesn't know, is the one with the little flag. And anyone who is a football or soccer fan, be interested to know that my town where I came from is the one where Ryan Reynolds randomly decided to buy a football team. So, yeah, shameless plug. In terms of my background and how I came about data science, I actually graduated from the University of Manchester with a PhD and Masters in Physics. Dabbled a little bit in programming during my time there, but really knew nothing about data science and wouldn't have really thought that I would pursue a career in it had it not been for my master's project my last year, where I was randomly assigned a project building classification systems in astrophysics to try and classify different types of stars based on how the brightness of the stars are clustered over time. They give me insight into sort of fundamental concepts like random classifiers, linear regression, regularization, and although at that point I was completely sick of physics, I was pretty interested by this new field that I'd been exposed to with a lot of people to try and see how it could be used in everyday life. And so once graduating, I was able to join Deloitte as a consulting data scientist. I did that for 3 years. And if there's any, I guess, benefit of being in the consultancy area, it's that you do get a lot of exposure to a lot of different industries. So I worked in a data engineering role within the finance industry. I did some time series forecasting for the health government in the UK during COVID, which was, really fast paced. And then as well, it's touched on some NLP and computer vision for the defense department as well. But very quickly kind of realized, I'm sure a lot of you will have the same situation, that the data science field is a little bit kept with the kind of assumption that everyone should have a master's. Constantly kind of found myself needing to prove that I was capable of doing the job. And so for that reason, as well as just wanting to fill in some knowledge gaps that were definitely accumulated through pure self-learning, decided to join the USF MSDS program. I forget which cohort. Are you guys cohort 13?
Yeah.
Okay, cohort 11. And yeah, I think it took like 1 week into the boot camp, specifically the stats class, for me to question what I would got myself in. But you know, made it through. It was a fun ride. I'm sure all of you can relate to that. But yeah, well done for getting this far, because it is most certainly not easy. And yeah, during the program, I was matched with PG&E as part of my practicing program, and then yeah, was fortunate enough at the end of that to be offered a position, and I've been there ever since, pretty much since September. So yeah, that's a very brief overview about me. And so yeah, getting on to the talk, versatile data scientist, adapting to diverse roles in small teams. Yeah, before anyone asks, ChatGPT did not write that. I was thinking about what to sort of talk about today, and I think for me, especially over maybe the last 5 years, kind of what definition of a data science role is feels like it's adapted quite a lot and expanded in some ways. You know, I feel like data science role can really be kind of categorized anything from business analysts with the more kind of business-based problems right through to, you know, kind of get research and sort of machine learning implementation at like an enterprise scale. And so especially when you're describing to people, it can be kind of hard to be like, what actually does data science entail? And I think specifically when you're working on maybe smaller teams, whether that's at a startup or within a smaller internal team in a company, at a large company like me, you often need to sort of have a broad range of skills to cover topics or tasks that can vary outside of the maybe normal data science experience, such as like data engineering tasks and machine learning engineering tasks. And so I thought it might be useful today to just sort of run through my experiences, the sort of short projects that I've been on, some of the tools and technologies I've had to use in order to sort of do my job. And so, yeah, before getting into that, it would be good to talk a little bit about who PG&E are, because I had no idea when I joined on the press. So PG&E is one of the largest utility companies in the US. They provide gas and electric to 16 million people across California, so it's the people you pay your bills to. Sorry about that. They are responsible for the maintenance and operation of significant amount of infrastructure. So in total, there's 50,000 miles, gas pipelines, 2.5 million transmission poles. So when you're kind of like driving down the highway, the wires and poles and all the components around it need to be maintained and in operation. As well as other things like electrical substations, and as well as power generation facilities such as like power plants, gas power plants, like that. And so you might be thinking, PG&E is a government-regulated utility. It's quite a large organization with like 4,000 people. It might not be the first place that you think that AI is completely embedded in, but you'd be surprised. There are a large number of teams, like the one that I sit on, that are doing a lot of cutting-edge research. Have some alumni here who are currently working on internship opportunities. We do time series broadcasting, anomaly detection, things like that. But one of the largest teams, which is the one that I sit on, is a computer vision team, aptly named the Waldo team. It's responsible for developing models for mainly two purposes. So the first one being to detect and catalog components present on those transmission structures, which drive traffic electricity across the country, as well as identifying any damaged components and trying to raise them for further repair or further inspection. So you can see an example here of a couple of the things that we have models trained for to detect. So, the purple boxes identifying the insulators which connect the live wires to the structure and sort of insulate them from the high voltage, as well as the components that connect those insulators to the wire and connect those insulators to the structure, as well as at the bottom, detecting sort of climbing guards to prevent people from climbing into structures. And the thing that really sort of facilitates our team to be able to do that is that PG&E contracts has a number of contractors who fly drones throughout the year, capturing aerial images of these transmission structures. And it ends up being around about 3 million images captured annually, and those are uploaded to S3. And that's kind of like the base of the data that we have access to in order to sort of address these challenges and start to build it. And so I mentioned I was going to kind of run through different areas and different sort of techniques in the job that I've had to adapt. And the first one being data engineering, and specifically around how we manage the labels associated with images, because as you can imagine, training computer vision models is very dependent on having adequate data sets and labeling the images which are captured by those drone operators. And so how do we do this? Primarily we use AWS. So it has its own internal platform, which is a pretty nice kind of GUI that you can send images to and have people log in and conveniently be able to draw bounding boxes on the images, click submit. And then once a particular job is completed, so you might send 1,000 images to be labeled within a specific job. Once those thousands have been labeled and the job is complete, then an output JSON file is kind of created and stored in S3. This is an example here, so it's information around the image S3 location, the image size, the annotations that were provided, like what class, what bounding boxes, etc. And when I joined the team, this was kind of the statement that, when you had a labeling job complete, you would need to sort of manually pull down that JSON, manipulate it, pull out the information, and create your data sets, which for all intents and purposes, it's fine, but most certainly not the most elegant solution. And what we had initially tried to aim for was to get to a point where we had a database that we could quite easily query to be able to pull down and create these data sets instead. And so, part of this was kind of sitting down, first figuring out what would be the schema of that database, see what the final product was here, and have labels tables with bounding box information, class information, an image table with the relevant S3 information, class tables with the relevant definitions, etc. As well as sort of additional metadata of what images were included in which jobs, and then a collection of jobs are associated with a particular campaign that is associated with a specific model you're trying to train. And so, once you are happy with this sort of schema, then it goes about the question of how do you actually implement this? How do you build this? How do you build this schema, and how do you start populating the rows? And so, I imagine from your SQL class, you could just go into terminal and manually, run create commands to create these tables. But on an enterprise scale, running these commands is probably not best practice, and maybe a little bit nerve-wracking, especially when going to delete things. And so what we ended up using was a pretty cool tool that would recommend in the future if anyone's doing something similar, which is SQL Alchemy. And what it allows you to do is define SQL tables, schemas in kind of a Pythonic object-oriented way. And you can see the example here. This is just one of the tables from the schema. By defining the class and inheriting from a base table, you're able to construct through class attributes the table name, what schema it's associated with, as well as defining the columns, its type, whether it's auto-incrementing, whether it's a primary key, whether it can be nullable, and pretty much anything that you could do within a SQL definition to sort of define these tables, you can replicate within this Pythonic interface. And the code at the bottom here sort of demonstrates once you've defined these classes, which represent your tables, how do you go about sort of creating rows and adding them to the database? And because your tables exist as a class, when you instantiate an object of that class, it effectively is a row within that table. And so you can see here, you're defining this particular campaign ID, so for, campaign name, new label, campaign, etc. And so once you instantiate that object and you initiate a connection to the database, you're able to then just simply add the record to the session and then commit that. And that will result in the database being populated with relevant tables. Very useful. It's a much more streamlined sort of process of how to do this. You can go through PR reviews and have it just be a lot more structured in terms of how to do this. So one more topic that one more sort of technology we wanted to discuss around data engineering was okay, cool, we have this software that we use to sort of create these tables, but how do we go about actually executing this code in order to sort of create tables? What we used was a technology called Alembic, which is kind of a subproduct of SQL Alchemy, and it allows you to perform migrations. And so I'm just quickly going to run through an example of what that migration might look like. So imagine that you have an existing kind of base employees table, and you want to make some modifications to it. So you might want to add some new employee records to that table. You might want to add an additional column that indicates what's the favorite food of the employees. You might want to manipulate columns to sort of combine two together, first and last name. Additionally, you might want to sort of delete records within that table. So you can imagine you're sort of building up this, similar to kind of a Git history within a repository, you're building up this sort of history of the states the database has sort of progressed through to get to its final state, I guess, indicated by that header. What Alembic migrations allow you to do is sort of make those transitions between each of the steps. And so each one of those steps is an Alembic migration. And the way that you transition from each step to the next is through a upgrade function, where you use the SQL Alchemy code that I was kind of referring to previously to define what you want to do. And you can use those kind of Pythonic objects to do that. But the powerful thing that Alembic allows you to do is not only do you have the upgrade function to transfer from one state to the other, you can also define downgrade functions to go from one state to a previous. And so similar to kind of Git, it now allows you to sort of traverse the entire history of this database in terms of, you could say reset the database back to its base employee table. And then later on, you can move it back forward. So it sort of emulates the Git functionality you have and be able to sort of version control your database, which is a lot better than just kind of running create commands in your Git server. And so, yeah, with those two tools, we went about sort of creating this database and populating it, and two sort of like streams of work emerged from that. So one, we had an existing backlog of these labeling jobs that we needed to sort of get into the database in the first place. This was done using those two technologies that I mentioned. So running lambda migrations to add each of these like 6 results to the database. And that code was kind of like created in a repository, peer reviewed, and then when a release was cut on that repository, then there was a Jenkins pipeline in the background that was able to run those migrations and perform those upgrades. But alternatively as well, there's kind of like, what do you do with the labels from future jobs? Like, you don't want to keep going back and manually have to run these migrations. And so we really wanted to kind of get to a point where when a job was completed within AWS, you could like automatically have it so that those labels were consumed, processed, and added to the database. And that's kind of exactly what we did. We used AWS tools, namely SQS, which is a queuing service. So when a labeling job is completed, it automatically kind of sent a message to this queue to be processed kind of later. And then those messages that were stored within the queue were automatically kind of processed by AWS Lambda, which you can think of as kind of workers which consume these messages, pull the results, the JSON results from S3, and then use this SQR meaning to actually kind of add the records to the database. And so, yeah, that was kind of the full workflow. I think it really improved our process of how we store and access data and made it a lot more kind of like redundant and streamlined. So the second one I wanted to go on to, which is probably, I would say still the bulk of my job as a data scientist, is kind of like around model development. I mentioned at the beginning, like the Waldo team is responsible for inventory categorization, but then also the second one, which is a much more newer stream, is detecting damage within components. That was kind of well, actually, yeah, I'll talk a little bit about how that's currently done at the moment, because, Waldo is just kind of an additional step on the infrastructure that already exists. So within PG&E, there is like an inspections team, which is, I forget how many people, I think around about 50 to 100 people, whose primary job is to sort of review these aerial images, one, categorize, and two, detect damage. And you can see the sort of interface that they have here. It's like an internal software that we use that they can, if they find anything in these images, they can draw their own bounding boxes. They can add like what type of damage they found, as well as like a severity level. And that's the kind of system that's existed for the last 3 or 4 years. It has worked well, but I would say, as you can imagine, with like the human workload needing to do that, they can actually only get through about 1/3 of the grid a year. And so you get this point where there's like a 3-year life cycle in order to sort of evaluate the entire grid for vulnerabilities, which is not the ideal place. So that was kind of the motivation for the Waldo team stepping in to try and like augment this process with kind of like 2 hopeful end goals. The first being, because it's kind of a machine learning model, you can plow through the entire grid within about the span of a week, which is a significant improvement, but it allows you to do 2 things. The first is to prioritize structures for inspectors to review at the beginning of a review cycle. And Waldo can flag, I think this particular type of damage is present in this image, for them to sort of go in and verify it. And then secondly, during the sort of inspection process, which will continue regardless, the predictions can be used as an aid to be like, okay, the model thinks there's something here. You should keep an eye out for this type of damage a bit more than you normally would. So that's the kind of motivation of how our team can kind of step in and hopefully augment this process. Now, as I mentioned, this is like a pretty new stream of work for us. And this initial model was kind of our POC to sort of figure out the extent that we could really add value to this workflow. And so, you can't do all damage at once. It's too many classes, it's too difficult. So I had to narrow it in. And the type of damage that we chose was something called flashing damage. And you can see an example here in this image. It's effectively where these insulators that connect the live wires to the structures, when there's like an intense electrical discharge from that live wire onto the insulator, it leaves these kind of scorch burn marks that you can see on the right hand side there. And what that does is it affects the component's ability to insulate the structure and can lead to further sparking and then ultimately to wildfires. And so kind of the modeling goal was to build an object detection model that could identify individual bells, and the bells are kind of described objects, individual bells that showed flashing damage. And so, with all of development, that comes with a number of steps. The first one, as with most cases in data science, implements a lot of those soft skills, so kind of coordinating with SMEs within the business to better understand this type of damage, understand like what constitutes it, what constitutes a severe type of damage, what constitutes like less severe, things like that, just to build out the full definition of problem statement. The second one is then building out a large enough data set that you can effectively develop a model. And it sounds simple enough, but it's actually extremely time consuming. And the problem that we did find with this model compared to others is it's really difficult to build a labeling guide where you're trying to like discretely bucket continuous damage. And like no two damages look the same. And so you have to build out like a really robust framework with lots of examples, lots of kind of like step-by-step guide, like look for this, if it's this extent, if it's like covers 60% of the bell. Like, it took a long time to get to this point. There's a lot of iterations to train PG&E's internal labeling team to get to a point where they were at a high enough accuracy that we were happy that we could progress to that larger scale of training. So once we were at that point, we were able to label about 10,000 images and get about 3,000 labels, which we found in the past is about and pretty much enough to develop a performant model. So once we were at that point, it was good enough to sort of like progress on to the next stage, which was to sort of train the actual object detection model itself. And technology's main sort of training algorithm we do use is detection, which is effectively a wrapper around PyTorch. And it kind of conveniently allows you to sort of define the configurations of the model within effectively a dictionary structure within a Python script. Allows you kind of like full control to tweak whatever you want. But interestingly, with all the models that we developed, we kind of found that the out-of-the-box pre-trained faster RCNN model typically works pretty well. And our approach to kind of fine-tuning performance definitely is more of a data-orientated in terms of like improving labels as opposed to sort of fine-tuning the model itself. Definitely for us has seemed the best approach. One thing that we did do, though, was we spent a lot of time modifying the inference process to try and minimize the model's false positive rate. And this was, I would say, difficulty number one with this whole model development has definitely been false positives, because all of the other asset detection models that we have running at the moment, you're trying to detect components which are fairly common, exist on most structures. And so, typical false positive rate of around 5% is probably not too much of an issue, because most of the images you're running inputs on will have components that you're trying to detect, and so most positive predictions will be true positives. But the issue with the damage model is the damage is so rare that if you have a non-negligible false positive rate, the end kind of prediction set, the majority of them are going to be false positives. And so, if you go to a stakeholder with a final report and you're like, here is the predictions for the entire grid, but sorry, 99% of them are false positives, it's kind of not really usable. So that was kind of the main focus for us. And after that initial training process, we were at around about 5 to 10% false positive rate, which fine normally, but most certainly not okay for this. And so we needed to sort of reapproach how we ran inference in terms of to try and push that number as low as possible. And the process that we kind of went about doing that was through data augmentation. And so you can see here with the original image in the top left, we effectively rotated and flipped that image to sort of get from a singular image, be able to get 8 different images. And the idea of doing this is kind of around when you pass an image for inference, the model can get it wrong. But if you pass kind of like 8 different versions of that same image, you're kind of increasing how many, you're making it easier for the model to make the right answer because it doesn't need to make the correct prediction on every single image. And so when you pass all these images for inference and you kind of like undo those flips and undo those rotations, you're kind of left with 8 different sets of predictions for the same image. Because, when you flip it and you pass it through the CNN, there's input pixel values different, and so it's going to propagate differently and it's going to produce different bounding boxes in the end. And so you can see from this example, there's some of these images, it's getting it wrong sometimes. This like prediction set 7, it's not correctly predicting the flashing, which is on that top bell. There's other ones where there's false positives on undamaged bells. But when you kind of like undo this flipping, undo those flips, and you combine them all together, you can start to kind of build up that picture of like, okay, overall the model is like doing quite well. Like for that top bell where there is definite flashing, it might get it wrong sometimes, but the majority of the time it is capturing the flashing. And so you can kind of get to a situation where you can do a bit of a majority vote effectively. The process of actually kind of combining those was a bit tricky, and it's probably a bit too much detail that's worth going in at this point. But you effectively like kind of group all of the predictions together for each bell, and you reduce it down to a single bounding box prediction. Just those bells. And this actually turned out to be an extremely effective method for us, and we were able to get the false positive rate down from about 5 to 10% down to like 0.1%, which, I think order of magnitude wide, it kind of meant that the end product to stakeholders was something that was actually very useful. And so, I mentioned that 0.2% in terms of evaluating the model performance. We're also getting an image recall rate of about 95, which is for us, we have internal kind of like standards of what we need to hit for a model to be considered performant, and that's sort of surpassed those for sure. Interesting thing we did find was kind of retroactively, once the model was trained, went back, compared it to sort of inspector performances. So inspectors historically over the last 3 or 4 years have built up a number of examples where they thought they found flashing damage and they've assigned an issue tag for this particular image. And when we compared their evaluations to the older models' evaluations, we found a big discrepancy. We found a significant proportion of the tags where Waller said there was nothing, but the inspectors were adamant that there was. And having internal specialists go through and make the final call on that, we did find that Waller was able to identify about 30% of the total issue tags as being erroneous, which was quite a nice benefit that I don't think we were envisioning when we set out. So again, proving the value of approaching this from an ML perspective. And then, so the final step of this is kind of around like how do you format and provide these results to stakeholders? Because the model influence, I guess, after you sort of develop a model, just have a weights file and a config file in S3, like it's not really useful. And so you need to sort of productionize that to be able to run inference at scale. And then also, once you run inference at scale, those results are just sent to the database. So how do you format that to be a useful asset for the stakeholders at the end? And so I'll talk a little bit more about productionization next, sort of the MLE kind of space. But we ultimately ended up having effectively an Excel spreadsheet that would just sit within PG&E's Palantir Foundry data platform. And stakeholders can log in, can use it, can access it, and augment that whole damage process. And so as I mentioned, it's kind of the last one. Goes too much longer, but and I guess the end stage of this whole kind of like development pipeline, which is like once you have a model, how do you actually make it useful? And so the platform that we have, we kind of built out significant AWS infrastructure to be able to very like at scale run predictions on all of our models for the tens of millions of images that we have. I guess the productionalization use case is going to vary depending on the company you're at. And, for some, live inference is going to be a requirement. So, need to have live results from images that you're sending to the model. For us, we're kind of like just required batch processing. Like we don't need that kind of like live feedback to stakeholders. And so we have built out infrastructure to be able to process those batches at scale. And that is primarily that. And I'll run a little bit through what that kind of automated pipeline looks like. So we have a worker AWS Lambdas function that's scheduled every day at midnight in a workday to query that aerial image database, and it finds all the images that were uploaded since the last time that this whole pipeline was run. It then batches those images up into chunks of about 200,000, and it posts the results of those messages to another queue within AWS for those messages then waiting to be processed. Then each one of those chunks of images is then consumed by another worker. It processes those images and it sends it to something called an AWS step function. And this is kind of like the main bread and butter of how we productionalize our inference. It effectively allows you to define a pipeline of how you want to process images. And I have an image that will come up in a minute that sort of details what that might look like. But the end result of a step function invocation is you have an inference script that runs inference on the images, and then writes those predictions to our Waldo's prediction database. And this is just kind of a screenshot of kind of the GUI definition of the step functions that we have. Each one of those blocks represents a specific kind of Python script that we run or a piece of logic that we implement, but they can kind of categorically be grouped into different functions. So verifying that the images you want to run an inference on actually exist, copying them to a specific S3 bucket that we need them to be in, then a chunk for performing inference and having it set up to be fault tolerant. So if for whatever reason the instance, the kind of EC2 instance that you're running the inference on goes down, we have the ability to kind of rerun processes, handle those shutdowns, and kind of minimize the amount of predictions that need to be run. And then with the final step of writing to the database. And so, this is just one of the pipelines that we have. This is actually just a pipeline for a single model. The ones that I've been talking about around the Insulate is actually, I don't think I could fit it on the slide. It's pretty big, but yes. So then, okay, yeah. So you're at the point where you now have predictions written in the database, but how do you then go from that to final end stakeholder report? And so what we also have is within Palantir Boundary, we have, again, another scheduled job that runs, I forget what time, I think it's about 9 a.m. each morning, that uses Apache Spark to kind of pull in the predictions that have been created and update the final Excel type form that's stored within Boundary. And then, that's accessible to stakeholders, and that is kind of flow that now runs pretty automated. And the code base associated with that is pretty human. And the tools used there, it's probably covers everything, but gives you a picture of the kind of things that are useful to know and will be used in these kind of tasks. So, CI/CD, you use Jenkins, Docker, Kubernetes, Git, programming languages like Python, SQL, Bash. ASL is like an internal Amazon state language that's useful for step functions as well. And then as well, a lot of cloud products that we've used that I've mentioned throughout this S3, SQS, etc. But I kind of hope that gives a bit of an overview of the type of roles, the type of technologies that can be used, especially with the smaller teams, where it's kind of important to be quite versatile and quite flexible in terms of your skill set, and constantly being willing to learn new things. I didn't know most of these when I joined the job. I just picked them up and curious and learned from people smarter than me. I think that was kind of the overall picture that I was trying to express in this talk, which was just be versatile. And I was going to leave it there, but I thought I'd be remiss if I didn't give some job search advice. I know Victor was saying I think everyone is supposed to start right now. So yeah, let's run through it. And I have a little stat sheet from my own experience. And who wants to guess? Who wants to guess the number of applications?
Oh, you have to say for international or domestic.
Okay, I'm international, so I think that makes it more difficult. Who wants to? Who's scared to know how big this stuff is? 400? 400?
1,500.
No, it's not that bad. It's about 600 applications.
Okay.
It's not bad.
That's what I thought.
That's a big number. I won't get you guess how many job interviews. You'll say that too high, too low. From the 600, I had 7 interviews, and from the 7 interviews, I had 2 openings. So that process was kind of spread out over a long period. So, starting now, you have a long time. And I have a list of kind of tips and tricks that I want to kind of like impart on you mostly through kind of like things that I've learned myself. First one is around like applications. So be consistent, be efficient, and don't get. So the consistency, like 600 seems big, but that's over like 2.5 months. And, you break that down, it's about 10 a day. And, that seems more manageable. So, just kind of allotting time and really just allowing yourself to go through those motions of finding the jobs and just find it. Makes it seem less daunting. The efficiency thing was actually kind of a big one because like it can be annoying to apply for jobs that can take a long time. I actually had automated as much as possible the whole application process. So I wrote 3 different very general versions of my cover letters, like one for D, one for DS, one for Emily. And I had a bash script. I would provide the company name, the job title, and then just fill in the blanks and save it and just upload it. So that helped a lot in terms of the time spent applying, which kind of means 6 jobs. That's not to say I did that for everything. If I found a job that I really thought looked amazing, I spent the time to customize, and sometimes I reached out to hiring managers or recruiters directly. That would be a really useful tool, especially if it's something you're super interested in. And then the don't be picky. I definitely felt this where I was like, no, I'm not going to apply for that. That was fine for the first couple of weeks, and then you very quickly realize okay, cool, I've done 45 applications, which I can't find any more. And so by the end of it, if I had the word data in it, I kind of applied for it. And it's a useful method because it really is a numbers game. You just kind of have to put it out there. And the benefit of applying to so many is kind of rejection is assumed. And anything else is a bonus. So, you kind of detach yourself from it, which is pretty nice. Next one is lead code. It's kind of something can't really ignore during this kind of application process, but it will vary depending on your goals. I would say tip number 1 there would be to simulate coding interviews, whether that's with friends or through online services as much as possible. Because there is a real big difference between being able to kind of bash your way through something just on your own in your mind on a laptop, as opposed to doing it in person in front of someone. I had the most long interview I've ever had in my life, where I kind of just rumbled for 45 minutes and didn't answer the question because it was horrific. So yeah, really prioritize that. And then as well, I would say, know the type of jobs that you're going to be wanting to apply for. I think the level of the code proficiency is going to vary depending on that. If you're kind of someone that's looking for more of maybe a business-facing data science role, being at a point where you can confidently answer easy questions and maybe medium is really fine. And might be wasting time to try to study more. But on the flip side, if you're going for maybe a harder, more Emily technical kind of roles, really knowing the fundamentals of data structures and being able to answer medium and hard questions, it's pretty important because you're going to kind of be found out in the interviews. And maybe another note on the kind of studying aspect, actually kind of writing down notes and writing down examples of your mistakes, it goes a long way because, I'm sure you've done this in the past, and you just kind of phrase up the problems. You might figure it out, you might look at the solutions, I'll remember that. But if you don't have like a dedicated list of like, this was the mistake I made, a trick I missed to review over, it just goes, it makes it a lot harder. So, focus on that. Next one, yeah, I think there's kind of an assumption within technical discussions that data science knowledge is pretty important. And I'd say the level of being at, it's like anything that's discussed within core core ML classes, like you never have sort of a technical discussion with the interviewer is pretty good. So I'd say being on top of that, that's pretty important. The next one that goes kind of hand in hand with that is behavioral and experience questions. So, how many data science projects you worked on, the challenges we've learned on. Having examples like first is pretty useful. Turns out it's pretty hard to make those open spot, which I also found out. And yeah, I would say as well, leveraging USF faculty, USF like resources was really useful. They have your best interests at heart. They really want people to succeed. I found it particularly useful actually during negotiations, which for me felt the most foreign part of the whole process. I mentioned that I had two job offers and things move very quickly. You get one, and I will accelerate everything. And all of a sudden, it'll feel like you've had months of nothing. And then you've got interviews every other day, and you're like trying to figure out how to battle each other off to get as good an offer as possible. And that was a big role, extremely useful during that process. So definitely make a student for that. And then, last one, just stay positive. Everyone else has gone through it and they ended out the other side. So, yeah, you guys come this far, you're all doing no sense that you'll make it through. So, yeah, there's a little bit of applied wisdom, and I'll hand it over if there's any questions.
Great. At this time, do you have any questions? Yeah. Sure.
Thank you so much for the talk. It's very exciting. Thank you very much for the tips. I have a question. When you were classifying the images and you asked a lot of people to classify it, did you ever think about using LLMs to classify images? Give them examples of how to classify more in a way like generating artificial data. Right?
Yeah, nice question. Should I stop it? Yeah, it's an interesting question. Like our process at the moment doesn't really incorporate anything like that, and it is something that we have kind of in the backlog to explore. And I think especially after pursuing this kind of the damage modeling, where it can be really hard to find enough data. Like this example we went through with the flashing, we chose it because it had the most data. Like it was the most common damage type, and there are damage types down the road where there are only maybe 100 image examples that we have on file, and we know when we get to that point, like we tools within that through LLMs or kind of like generation. So yeah, well, we will. Yeah, thanks.
Hey, my question is like, thank you for talking. My question is regarding like the number of applications and everything you did. Were your offers and like those applications, did they count like by reaching out to people, or were those all like LinkedIn applications or like through your websites and stuff?
Yeah, I would say the majority of the applications were LinkedIn, or through job boards, just like apply button numbers, resumes, etc. I did apply, like I mentioned that I did reach out to recruiters and stuff at job sites I'm interested in. I think it led to like one interview, I think. But yeah, not really with the others. So yeah, maybe actually that does spur another thing that I did want to mention. I don't know whether you still have access to the same software of like saving the job information when I create.
Yeah, but only half the students liked it, and the rest complained about it, so we just stopped it.
I love that. Yeah, good. I definitely had it where someone would reach out and say, I didn't know that it existed. But no, that's a good question. Most of them were through.
Oh, thank you.
I think that's good. Yeah.
Hey, thank you so much for the talk. My name is Nick. I had a question about model choice with image segmentation. Was like complexity ever a consideration for you guys? Like I know there's newer like transformer-based models that out of the box perform better than typical CMNs. I was wondering about your choice of how to pick it.
Yeah, it's a really interesting one that I think was a bit of a jar going into kind of like industry developing at scale where there is a trade-off between, achieving the best performance and kind of like doing like taking longer to do that or taking shorter time to reach usable performance that you could like, intrinsically bang out on. And this project's been around for 5 or 6 years, so long before I've been there. And this was kind of the framework that we had found that we can achieve 90+% precision using out of the box pastoral CNN. And so that is kind of the process that we just have. It's kind of the representation of like have develop a V0 model with this and promise that it don't really need to kind of pursue further because there are other priorities that the models develop and it's just that kind of bandwidth. Do I get really responding that like this just sucks like we need to look at other avenues. So yeah, there is that real trade-off and we haven't really looked into other aspects.
Thank you so much.
Hi, Georgia. Thank you, Matt. Question about what it was like working on a team that had such a large task, right? With a lot of like government oversight, regulation, responsibility, and just the scope of the project. What was it like managing things like tech debt, timelines? What was your experience there? Maybe like a sticking point or a pain point?
Yeah. I would say the tech debt point is a really interesting one because at scale with this number of models, like tech debt is inevitable. And a lot of the things I think I ran through, especially with the label management and productionization, a lot of that framework came out of addressing tech debt. Because previously, we would have everything extremely manual and we just wouldn't be able to run at scale. So tech debt has been something that we really addressed, particularly in the last 6 months. In terms of like the wider scale, it's quite nice to have quite a bit of insulation from a lot of those internal politics through tech leads being able to have that PMs managing more interactions with stakeholders because the internal politics is pretty intense in terms of like navigating funding. There's always a constant battle of like other stakeholders within the business wanting to pursue external vendor solutions instead of developing internal. And I do not have to do that.
Hello. Okay. Thank you so much for the talk. One thing I really appreciate about your talk was the idea of small teams and the ability to wear multiple hats. One thing that I was wondering about is how much space do you have to sort of grow and learn those skills? How much of it you sort of came in with? I do recognize a lot of the technologies and things that we did learn here in MSDS so far. And so how is that growth culture like? And also, how have you found mentorship in a small team?
Yeah, I mean, having only really experienced kind of a singular team, hard to generalize, but I think I feel pretty lucky in terms of the team that I've kind of sat within. In terms of mentors, I have, 2 very experienced tech leads that I kind of like work collaboratively with. And in terms of like what skill set I had come in, most of those technologies that I mentioned, I really had no experience with. Like, effectively, my experience is what you guys have in terms of exposure to the classes, proficiency in Python and SQL, concepts of machine learning, how to do performance work. But in terms of working with like CI/CD stuff, cloud infrastructure, all of the language migration stuff that I mentioned, like that was all learned on the job and learning off of people who have experience using this. And I think if you make time and are kind of very vocal about like I want to learn this. Like for me, I think the direction where I want my career to go is more in that kind of productionization MLE space, and I've been vocal that I want to upskill in this. And the team has adapted to that and has provided me the opportunity to learn, to prove myself and to learn off others. So yeah, it's just kind of being an advocate for your own development.
Thank you very much.
Nice.
You talked about that like 30% wrongly finally like flashing. I was kind of curious what kind of like the process was to settle that kind of like disagreement, and kind of like was there like retraining that had to be done, or was that kind of that?
Yeah, so I think that was an interesting result to come across. Effectively, what it meant was the 30% of those kind of human generated labels were incorrect. It's the kind of like overarching goal of that. And the results of that were when a tag is created, it's passed off to a downstream team, which then like further reviews it and then goes out into the field and like manually corrects the error and like fixes it. And so for those erroneous ones where it was like, okay, yeah, no, this is incorrect, they would either like call further downstream by like a more experienced reviewer, or when it came time to review, they were like, let's fix. And so really there wasn't actually too much of like it being anything negative towards the model we developed. If anything, it was quite a positive sign that the additional value add that we can have, which is the process can be improved and can be augmented to a point where the performance is a lot better. Yeah, I wouldn't really say that there was anything for us. It was kind of self-congratulations. Honestly, we're like, oh, it's pretty good.
So were those like people in the field that were like making mistakes? Is there like reteaching them about like what it should be?
No, not particularly. Like, say about, so basically, I would say for that, it isn't really like a negative view or impact to those people purely because just of the workload that they're under. Like I mentioned that they can only review about a third of the grid a year. The time and like the pressures that come in terms of like being able to check, not just for one damage, like this is a singular damage that our model looks at. They have to look at hundreds. On top, like every image they look at, they have to keep it in their mind that they need to look at at least 100 different types of damage. And if you imagine that's a tough task. And there's going to be errors, and it's just kind of human error at that point. And it's kind of accepted as a reality within the business that it just kind of exists, and it is something that's hard. And was really the main motivation for trying to sort of augment that with AI to try and improve the accuracy with it. So, thank you.
All right, thank you very much. We will end there, and then if anybody has one-on-one questions, please come up and talk to Matt. So much, everyone.